So let's try this again. So you would have already had this graphed. So I'll draw that in real quick. So we said x cubed for this. We just wanted this part, and then here's y equals 2, x equals 0 is the y-axis. So this is our original space, and then I wanted to do the same thing over here. Where here's kind of the x cubed graph. Here's y equals 2. Same space. What I then had you do is talk about how and draw in. We can either have vertical or horizontal rectangles. So I wanted you to draw the horizontal on this side and the vertical rectangle on this side. And then what I asked you to do is rotate those. Think about when I rotate those, which one, the left or the right, would produce a disk if we were to rotate that, right? Since that's what this one was asking for. So hopefully we understood. So a lot of heads nod when I asked. When this rotates around, it's going to reappear over here. And this rectangle getting rotated is what creates our disks. Okay? But what you have to now understand, and this is the biggest key to keep straight with all of this stuff to make this pretty manageable material, is that as soon as I go horizontal, which this disk would be, when I now go to ask you what the width of these are going to be, because let's go ahead and set up our disk now. So let me do that real quick. So you're going to have pi r squared and then dy. The reason that we have to have a dy right here is because when I ask you what the width of this circle is, or the radius that I'm going to draw in here in a minute, or the original rectangle, let me just erase the circle, right? This rectangle right here that we rotated, when did this rectangle have a width defined as the change along that y-axis? So that is why when you're going to go horizontal, we always end up doing this in terms of y. What that now requires us to do, when I go to define this radius right here, the right-hand side of that radius is this curve. So this was the curve y equals x cubed. Our issue is we can't plug this in as y equals x cubed because these then don't match up. One's in terms of y, one is in terms of x. So since we know horizontal has to be done in terms of y, that means we have to rewrite the x cubed curve as x equals the cubed root of y. That's what this equation looks like with respect to the variable y. The left-hand side is the y-axis, so that's easy. That's going to be a 0. But that now is the cubed root of y minus 0, and then that's our radius that we're going to square. Your limits then also now need to be y. So if we understand that, think about what y value our first disk would have been drawn into. It would have been drawn in way at the bottom down here, so that would have started at the y value of 0. And then we would have continued to draw in circular disks as we continue to pile them on top of each other until we get to the very top right here. That was the line y equals 2. So that one, our y value is 2, where that area would have ended. So in terms of number 4, that's the answer to number 4. That's what I would have wanted you to do. That's probably what you see on the answers that I provided. That's our setup. Let's, however, go over to the right-hand side and say that we've rotated this around the y-axis, but we had a vertical rectangle in here. Because in reality, if you were to choose the best method, the way this is written would imply a vertical rectangle would have been our preferred method. This is actually our preferred method. So I'm kind of forcing your hand a little bit here to see if we knew how to rewrite some things. This would be the method you would pick if we were still dealing with numbers 1 through 3, where I said determine the best method. So let's go ahead and do it this way now. We see that when we take this vertical rectangle and rotate it, it would have reappeared over here, going around the front, side, and back. That's then forming our cylinder. So when we now go to set up our cylinder, we're going to have our 2 pi, our radius, our height. So that's our radius, our height, and then our width. The reason anything vertical has to be dx is because the width, if I now look at my red marker, if I could extend that down to the x-axis, I'd be looking, how much width do I take up along the x-axis? So the width of anything vertical is going to be the dx. The height, if I look at this segment right here, this is my height. It's bordered on top by the line 2 and on bottom by x cubed. Now we don't have to rewrite that equation because we're dealing in x's. The radius is right here. The right-hand side of the radius is this vertical line x. We don't know what that x value would be, but that's the right-hand side. 0 is on the left. So here's 0. Our limits now need to be x's. So since I now have x, 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 my lower limit and my upper limit need to be in terms of x. And again, when we're dealing with cylinders, make sure you're only defining your limits for the original space. So the original space definitely starts at the x value of 0. And then we would want to know, where does this original space end at? We would want to figure out the intersection point of y equals 2 and y equals x cubed. So if we solve that real quick, you'd have to do the cube root to both sides. And the cube root of x, what am I doing here? 2. The cube root of 2 ends up being our limit for the right-hand side. If we throw these into our calculator, so if you do a math 9 on this guy, if you do a math 9 on this guy, we'll give you the exact same answer. So this is our preferred method because of the way it was written, and this is the way that I was asking you to do it, just to see if we could rewrite it and understand how that works, okay? The reason I wanted to get to 5 and 6 is because these are our cross sections, and we haven't done these in a little bit. I didn't put these on that homework when we were just dealing with the rotations. So the cross sections were the ones where if I give you this curve, so let's draw in x squared plus 2, so a vertex at 0, 2, parabola that opens upwards over the interval of -2 to 2. Go back to when we first started to define these. If I ask you for the region enclosed by just one curve, if you're not given 2 curves, it's always implied the other curve is the x-axis. So that would mean we're dealing with the curve, the x-axis from -2 to 2. So this is our space. So what we've now been doing for a while, last 4 or 5 days, we've been taking this space and rotating it. If you remember when we first started these, we didn't rotate it, we just took that space and we put things on top of it. That's what we're talking about when we're dealing with these cross sections. When you read it, we always want to know that if we're perpendicular to the x-axis, we're putting these in vertically. The x-axis is obviously horizontal, so our cross sections go in vertically. Our cross sections for this problem are going to be semicircles, and we want the diameters on the solid of the base. So we want the diameter on the blue region or on your paper. So what we did when we did these is we first talked about, let's draw in a semicircle, a vertical semicircle. So our diameter is vertical. So there that is. We're going to take this, we're going to place this flat side on our space here, on your paper, on the blue region, the flat side. The circular part is out in front. I'll draw a few more. There's another one that I'm putting out there. Draw one more over here. So the back of it's flat. That's the diameter lining up on your paper. And then the front side is the curved circular part. The area of each one of those, if it was flat, since it's a semicircle, is 1/2 pi r squared. But each of those has a width. So if I look at this diameter here, here's the width of this one. Notice how it's the change in x. So when we define our width, or give it a width, now we're jumping to volume. This gives us the volume of any one of them. We don't want the volume of one, we wanted all of them. So that would be what we set up for this particular cross section. So for this one now, in terms of all the information we would need, we're going to have our 1/2 pi out in front. We need to define our radius, square it, and we need our width. Like I just said, the width is the change in x. Anything vertical is x's again. If we now draw the radius into all of these, so here's the radius of the middle one, the radius of the one on the left, the radius of the one on the right. The radius is now a vertical segment, so I want to define what's on the top of all of these circles and what's on the top of every radius. That's easy. The top of every radius, so if I try to define my radius, the top is going to be the parabola x squared plus 2. But then I still have to do minus the bottom. If we look at the bottom of all of these radii, there's no curve, no function bordering the bottom of our radius for any of those three that I have drawn in. For the one that you have drawn in, there's nothing on the bottom. So this is a one to where if we're going to have to come up with a bottom here, which we need to, we're going to have to draw in the diameter. So just extend this all the way to the x-axis, which is just y equals 0. Now we have a top. 0 is the bottom, but what we have now just done is define our diameter. So that's our diameter. And then we would now know our radius would have to be that expression divided by 2. That's what gets substituted in for the integral. All right. Since we're defining this all in terms of x, we want to know what x value does that region begin at. It's pretty obviously a -2. And what x value does that region end at? That's a +2. So this is what you throw into your calculator. All right, that's our setup. That last cross section here says the base of a solid is a region enclosed by 2 minus x squared and x squared. So 2 minus x squared and then x squared. So the region enclosed is this space. I don't think I gave you first quadrant. Nope. So we want all of it. This one's a little different than ones we've done before. I want this to be, what am I doing here? Isosceles triangles. So we definitely have equilateral triangles. So look that over. Equilateral triangles are this. All right, those are the easier version. Isosceles triangles don't have a special formula, so we would just want to know the area of an isosceles triangle is the basic 1/2 base times height. So think about an isosceles triangle here. So I'm going to take this triangle and I'm going to move that over. So I'm going to take this, I'm going to slide it over. So when I do that, I'm going to put this side here on the base, knowing that this side and this side have the same length. So if I do that, that's the one of the congruent sides. What you have to understand is this vertex here is pointed out towards us. It's pointed right at your nose right now. When we draw it in, we can't really do that. So it's going to kind of look like it's out here, but just know that that's pointed out towards you. And then this is congruent to that side. So each of those has a width. My pen again, so that's why it's a volume. We want to add all of those up. So for this one, you're going to have just a half out in front because it's 1/2 base times height. We need to define the base of our triangle. We need to define the height of our triangle. And then our width, since we are vertical, you can see the width of my pen would be the change along the x-axis. And again, this is the one that's actually on the curve. This one is not. The base is what our triangle sits on. So this is our base right here. So look at the top of that, look at the bottom of that. The top of that curve is 2 minus x squared. Or the top of that segment is 2 minus x squared, and then x squared is on the bottom. And then to determine your height, now this really kind of challenges us. Do we really understand what this figure looks like? What you have to understand is this segment here, if we actually have this little dot pointing at your nose right now, this segment actually is the height. That would be how far off the paper that your triangle is extending, pointing up towards you. So the height is that segment. That's also the congruent side to our base. So whatever our base was would have to be the same thing that our height was. Since it was an isosceles triangle, they have the same lengths. Since we have x's everywhere, Our limits need to be x's, so we need to know what x value here and what x value here do they intersect at. So take those two equations, set them equal, and we should get plus or minus 1. All right, and then that's our guy. Now, I will not give you an isosceles triangle tomorrow, so I wouldn't freak out about that. But certainly all the other geometric shapes that we've dealt with, so if you look through 7.3 day 1, that's where these come from. So we did circles as a cross section, semicircles, which we just did one of those in the previous problem. We did a square, and we did equilateral triangles. So look those over, make sure you can handle those. There's going to be 1 or 2 of those on there. Again, any questions for me, check in with me tomorrow morning before school. I'll be on our classroom link at 9:30. All right, so good luck. Let me know if you have any questions. Have a good night. See that.